Welcome to this lecture on using GLHE Pro for ground heat exchanger design. In this lecture, the main goal is to introduce the use of GLHE Pro for designing a ground heat exchanger, and I'll say with a traditional ground source heat pump system. So this is one where all the loads are handled by ground source heat pumps, and we don't have any cooling towers or fan coil units using free cooling in the summer, but just sort of conventional system, at least here in the U.S., with distributed water-to-air heat pumps, although it won't necessarily be that much different from another, say, a system with water-to-water heat pumps, but that's what I'm going to do an example here. So this lecture relies on some other lectures I've already given. So there was an overview of ground heat exchanger design with GLHE Pro. There was a lecture on treating loads in GLHE Pro. There's a lecture on modeling heat pumps in GLHE Pro, and a lecture on design and modeling of the borehole in GLHE Pro. So in this lecture, I plan to sort of cover a few remaining things that we haven't discussed yet, and then I have an example. Okay, things that I plan not to cover here. Hybrid ground source heat pump systems, horizontal and slinky ground heat exchangers, the free placement finite line source ground heat exchanger model, which you can use for up to 30 boreholes, but you have to place the boreholes. So we're just going to use the library of G functions for different borehole configurations here. And standing column wells, I'm not going to cover. Hourly simulation, I'm not going to cover. Well, there's probably other things I'm not going to cover, but those are the things I'm explicitly not going to cover. So this is just traditional ground source heat pump system, vertical boreholes. And this is the example will be for a larger system, commercial scale. Okay, so I plan to talk about a few things that I haven't yet covered. This includes undisturbed ground temperatures, fluid types and flow rates, temperature limits for sizing, and a little bit about design workflow. And then I have a demonstration. So if we start with undisturbed ground temperatures, the first thing to know is for vertical boreholes, we typically are really only using a single mean value. All right, so it's true the temperature varies over the year in the ground. It varies a lot in the first meter or 3 feet. It varies, you can see a little bit down further to 15, 20 feet, but if you get much deeper, it's very hard to detect the difference over the year. So if you have a borehole, let's say 75 meters or 250 feet deep, what's happening in the top meter or top 2 meters probably has very little effect, especially since, at least here, we typically, the top of the borehole is typically down, say, 4 or 5 feet, so 1.5 meters. In terms of determining this, probably the best approach is to estimate the best approach is, I think, a downhole measurement, where you, sometime after you've done a thermal response test and all the drilling energy subsided, you lower a thermocouple or other temperature sensor downhole and make measurements we used to do it every 10 feet. Another way of approximating this is typically when we do a thermal response test, we'll start circulating the fluid, so the only energy going in that point is the circulating pump. And if you record the data frequently, for say 3 or 4 times circulating through, you take the average of the temperatures that you measured, you get a reasonable idea of the undisturbed ground temperature. That's another way to do it. GLHE Pro also has a method for estimating it if you don't have thermal response test. The method is based on a model and a large database. So, and it's for truly undisturbed ground temperatures. So specifically here, one's not affected by urbanization, by buildings or pavement. If you have a shallow horizontal ground heat exchanger, right, GLHE Pro can also predict the temperature as a function of depth and day of the year. It's really a bit beyond this lecture, but if I have a chance to do one on horizontal ground heat exchangers, we'll bring that back up. Okay, so the model in GLHE Pro is based on this work done by my PhD student Lu Xing. There were 3 papers on it, and they'll be in the reference section. Used 4,112 sites worldwide, and estimated parameters for well, it's a fairly simple equation that it uses, but it can estimate for the time of the date of the year and the depth. Right, and I plotted 2 different days, so this is January 1st, this is day 179, which must be near the end of June. Right, and these are the temperature predictions. And you can see, yes, there's quite a bit of variation at the top, but if we get, say, below, well, in this case, below 10 meters, right, you can see that it's just about constant. Right, and this model also does not account for the geothermal gradient. Right, so if you actually make downhole measurements, you'll see that as the borehole gets deeper, rather than this staying constant, it actually has a slight upward slope. Ones that we've measured here are about 1 degree Fahrenheit per 100 feet, which comes out somewhere around 2 degrees Celsius per 100 meters, maybe not quite that high, but something like that. So this is a reason to have a downhole measurement rather than just taking it from here. It's also true that if you have an urban area, so if you look at a profile measured, say, in Stockholm, right, sorry, I got interrupted. So I think I was saying for Stockholm, for example, we have some measurements. You can see the urban effect. So this is actually an example from a paper by Singeld Jolin and myself and Joran Hellström. And these are based on measurements in Stockholm. If you ignore this line here, this is would be the average temperature over the borehole depth given the temperature variation. So this is the actual measured temperatures here down to almost 900 feet, so it's quite deep. The red line here is about what we would expect for the Stockholm undisturbed ground temperature. And this part here, right, this is what we see as the effect of urbanization here. And then down here, you see that sort of straight line. This is what we call the geothermal gradient, which, let's see, it's changing. I don't know if we can find a good place on here, but from, say, 300 meters down to 600 meters, it's changing about 4 degrees over 300 meters, so that would be a little, what, 1.33 degrees C per meter. So that's, of course, we only have measurements down to here. These are just extrapolated from this here. So there can be an urbanization effect, and that's the reason why the best method would be to actually make a thermal response test. Okay, the actual interface in GLHE Pro, we'll look at this later, but this is the interface. You say choose soil properties or soil temperature, I think, and you can choose for different continents. You can search the table. You can see you can actually see the temperature profile if you'd like for a specific day or at a specific depth versus time. Okay, when we do a live demo, we'll come back to that. And then GLHE Pro will take a range of fluid types and flow rates. So for pure water and then mixtures of water with propylene glycol, ethylene glycol, methanol, and ethanol, we have a model of all the properties built in, so it can tell you for specific fluid mixture, what the freezing point is, and for a specific temperature, it will give you the density, volumetric heat capacity, the conductivity, and viscosity. And what you should do here is GLHE Pro uses one value of borehole resistance for the whole design. You'd really like to set that near the design constraint. So if you're constrained by maximum entering fluid temperature, then you should set the mean temperature near the maximum entering fluid temperature. Or if you're constrained by the minimum, you should set it near the minimum. So 20 degrees C is probably in between. How much difference would it make? If you stay turbulent all the time, it won't make a huge difference. If it, as is possible, if you drop down into laminar flow under cold conditions, it may make a bigger difference in the size. If your antifreeze mixture isn't here, we have a library. You would have to add, well, we actually have some other types of brines. There used to be an antifreeze called GS4. I don't think it's commercially available anymore, but we had some properties for it, or you can add your own. Okay, when you actually go to size of ground heat exchanger, you'll choose the configuration. For example, a 10 by 10 field of boreholes with 100 boreholes. You will specify everything about it except the depth, and then you'll use the sizing function to find the depth. And if you find it's too deep or maybe too shallow and you'd like to go deeper, then you can choose a different configuration. So the temperature limits, they're set by the user when sizing. They should in general be consistent with the heat pump unit selection. So when you select a heat pump for a zone, say it's maximum cooling, you have a maximum cooling load, in general, I think you should be your heat pump should have enough capacity to meet the zone load when you're at this maximum entering fluid temperature. The maximum entering fluid temperature and the maximum load for any zone may not coincide, so there's some margin of safety by choosing making sure you can meet the capacity at the maximum temperature. But in general, that's what I'd recommend. And in terms of recommendations, a typical recommendation, this is found in a paper by Lisa Moline and Steve Kavanaugh, is that the maximum entering fluid temperature of the heat pump, for cooling conditions, should be somewhere between 20 and 30 degrees Fahrenheit above the undisturbed ground temperature, or 11 to 17 above the undisturbed ground temperature. And when I say, undisturbed ground temperature here, I guess I'm using this slightly differently. This would be the ground temperature that you've input for the ground surrounding the borehole. If you had urbanization and if you measured the actual temperature and put it in, then you would use that, not what I was calling the undisturbed, by meaning it was never any pavement or anything like that. Maybe I should just call that GT. Well, nice thing about giving lectures like this is we can fix it. There we go. So whatever your ground temperature is that you're using, it should be somewhere in that range. Minimum somewhere between 10 and 16 degrees, or between Fahrenheit, or 6 to 9 below the ground temperature. Now these are really starting recommendations. You can possibly go outside these ranges. But one reason to use this, or for me to come out and say this explicitly, is occasionally I've had users contact me about GLHE Pro. Oh, I'm getting these really deep boreholes. This just something must be wrong. And then I find out that they're in a location where, say, the undisturbed ground temperature is 70 degrees Fahrenheit, and they've put in 75 as the maximum temperature, right? The closer you put your maximum and minimum to the ground temperature, the larger the ground heat exchanger size you're going to get it's going to be. Okay, so a little bit about sort of workflow. I mean, this could be done different ways, but typically you would determine the hourly heating and cooling loads on heat pumps for a typical year. Ideally use a thermal response test to determine the ground thermal properties, the drilling conditions, and the ground temperature. You'd select a minimum maximum heat pump entering fluid temperature, and once you've done that, then you can select the heat pumps that'll meet those loads. And you may may apply corrections to what the manufacturer gives in a standard table. Let's see, we've done that in our example on the modeling of heat pumps, right? So the standard, in that case, the standard return air conditions to the heat pump, where I think we're 80 degrees Fahrenheit. That was the temperature, which is a bit high for typical North American practice. So at least if you're not mixing in outdoor air with it. But in any case, you'll choose some heat pumps, and then once you've done that, you can size the field, you can adjust the borehole spacing, the design of the borehole, and other factors to minimize the required drilling and overall costs. Okay, and plan to do this in part 2. I have not written this out yet or recorded it yet. And that would be, you should definitely check the hydraulic efficiency and to make sure that you don't have excessive pumping power, and you should check the system efficiency. Yeah, an estimate of the overall efficiency. I'll discuss those later, but I haven't done that. Haven't prepared that yet.